Hey, I'm Dave. Welcome to my shop. This is part 3 in the software code review of my ESP32 single-chip spectrum analyzer, where we take an in-depth look at how the software to drive the project is constructed. In this final installment, we'll be looking at the details of how the spectrum display class actually draws the entire spectrum display. It knows nothing about audio or math and simply is given a set of 16 values that range from 0 to 1 that represent how high each bar is. Its job is to use the LED matrix graphics class that we saw earlier to actually construct the on-screen display of the spectrum bars and the VU meter. It also manages decaying the bars over time and fading the white highlights in certain modes. At the very end, we'll flash the chip and boot it up to make sure the code we've cranked out actually functions. So if you're ready, I'll put the programming jacket back on and I'll head into the Oval Office to wrap up the conclusion in the final code review installment.
And last but not least, the fourth and final piece. The spectrum display. Just for historical purposes, if you're curious why it's spectrum display IRQ in the header files, I wrote two versions. This is actually the second version. The first was a non-interrupt driven one that simply did it iteratively and did not work as nicely, which led me to write the interrupt driven one, which does work nicely, hence the naming. We need two small definitions up here. One is shade band edge, just to turn off a little piece of code that was intended to give some depth to the appearance of the bands, but did not really do so, so I just turned it off with that. Peak 1 will be the rate at which the white highlight falls on the display, and peak 2 is the rate at which the bar itself collapses or falls back to earth. This is in panels per second, so the reciprocal is your time. I can't do that in my head. It's going to be just under a half, so 45 repeating, something like that. Going from there, we need to take a look at the peak data class, because that is the data that we've been returning, but is finally defined in this class. So now we can take a look at it with some greater detail. Take a closer look at peak data here. Peak data is simply a packed set of band count, being the number of bands you have, floats. And so if you have 16 bands, it's 16 floats. Each one is merely a 0 to 1.0 value of how high that band should be drawn on the display. That's calculated by the sound analyzer, and it's going to be stuffed in here by whatever the opposite of poking, I guess. In a few seconds we'll see that. And all we know so far is that there's a class called the spectrum display that gets passed a peak data. So we need some way to set these peaks. So let's add a function to do that, corresponding to what we already saw called in the other file. So take one of those peak data objects, run through it, and if the peak on the peak data object is greater than what we internally have as our last, best, highest known peak, then replace it. And when we do so, keep a timestamp. That's so the white line can decay at it affects the visuals, and we'll explain more when we get to see its use, but we only record it for the peak one. So let's flesh out the spectrum display class a little bit, the old skeleton of it. It's going to need to know where to draw. So it has a reference to an LED matrix graphics object, which is representative of the LED panels. It also needs to know the number of bands. It doesn't need to know width or height or anything like that, because it can always ask the panel. Peak data is where it keeps track of its peaks, and last peak time is where it keeps track of the time that the peak was last recorded. The constructor is simple enough, simply takes the reference to the graphics panel and the number of bands and stores them away in the object state. Now you saw here where we set the peaks, we also need a function to decay the peaks. It's in the private section because it's not called from outside the class. It's done internally when the frame is drawn. Let's take a look at how that is done. It looks at how long in seconds it has been since it has last been called, multiplies that by the rate at which it's supposed to fall per second, and decays each value by that amount. Let's jump back down to the public section of the file to add our draw code. Draw each band. And now I know why I don't type live. Okay, so the first thing we do is fill the screen, which feels very deja vu to me. So I'm going to say, bug, is this redundant perhaps? Because I think the caller actually does this. Regardless of who clears the screen, the drawing is done by iterating through all 16 bands and getting a color from the color palette for this object. We'll talk more about color palettes in a moment, but just know that we draw a band by calling it with its band index and a color, and that color is pulled out of a palette based on its position in the band order. It then draws the VU meter and decays the peaks as we saw. So the palettes are a fast LED notion, and basically you can think of them as a 256 byte color scheme laid out linearly. So actually a 256 color scheme. So I am grabbing basically the band number times 16 plus the base hue, all modulus 256, into a 256 byte array of colors. And there's more to it going on because it's actually extrapolating and interpolating, I believe, behind the scenes, but you can think of it as just a big array of colors. Now, if drawing is just a matter of drawing a band, who's doing the actual work? And that is, of course, draw band. It is back up in the private section since it's not called externally. First thing it does is calculate two values. Which one is value, which is the level of the white high line, and value 2, which is the level of the bar itself. One thing I noticed here is I've got some defensive programming. Never should be outside the height in either case, so we should either be asserting that it doesn't happen and letting it through, or fixing the cases where it does happen, or just removing this check entirely rather than letting it randomly draw anywhere. I mean, we are not an operating system, we should be responsible for where we draw. I guess, which is not to say that I necessarily would always remove these because they do protect you, but I would certainly want to know about the cases where they're being invoked. So bandwidth is the width of the matrix, which is 48 LEDs, divided by the number of bands, which is 16, so 3 LEDs per band. And if that's the first thing that made sense in a while, thanks for sticking with it. The next is the X offset of the band in LEDs. Y is where to start drawing the highlight based on the height of the matrix and the value that we're drawing it up to, and Y offset 2 is where the bar starts. We draw the bar in a scanline fashion, walking through it and drawing each line one at a time. This is to accommodate some of the earlier effects, and iRow, which is no longer used, is indicative of which scanline of the bar you're currently on. The shade band edge was to give the right-hand side of the bands a slightly darker color hue, but it didn't actually look convincing. It did look kind of interesting, so I didn't want to throw it away entirely, so I just pound-defined the code out. Peak decay, or peak fade time, which really should be moved up to the top of the file, is the time in milliseconds that it takes the white peak to fade away, which is 1 second. And so it fades from white through to black. And if it is 0, it goes back to the color of the bar itself. If the peak decay has been cranked all the way to 0, then the line is not actually drawn for the highlight at all. Otherwise, it's drawn in the highlight color. So by respecting when this number goes to 0 and not drawing the line at all, we give you a way to turn off that feature entirely with a simple knob turn. And last but not least, the VU meter. So the VU meter is not a stereo meter because we are not sampling in stereo, we're sampling only one channel. So it kind of cheats and it draws it outwards in both directions, but it is a mono meter. So the first thing it does is fill its little rectangle, which is just one line, with black. Here's where we draw the VU peaks, if there is one. We know if there is by having a greater than 1 value. It would be greater than 0, but they're 2 pixels wide, which is the reason. Fade is the amount to fade that pixel out, and so we draw it and its little buddy, 1 by 1, because it's 2 pixels wide. Can't do a loop for 2 pixels. X half is a maximum we could be. It's half the width of the whole panel, and bars is the amount that we actually are. And a little more defensive programming here, it looks like, to make sure that we never go over half. That I'm less confident about because I don't know where GVU comes. Well, I know where it comes from, but it's external to this function, so it probably should at least be somewhat sensitive to it, I guess. I'm uncertain. I'll come back to that one. And the very last thing we need is the function to actually draw the pixel for the VU meter. We're going to set an LED pixel. We figure out, we know the X position, we're given the Y, the amount to fade by, we know what half of this meter is so that we can go out symmetrically. We look up the color palette, which is a palette that, as we mentioned, goes 256 bytes, and it fades from red through green through yellow, and then back to red. But it starts with a dark green so that the innermost pixels are kind of dimmer. And if you see it, it makes more sense, but it actually works pretty well. And it's as simple as draw 2 pixels here. And at first I thought, oh, why am I drawing 2 pixels? I called it twice, but remember, it's 2 pixels twice. Once for the apparent left channel and once for the apparent right channel. So 4 pixels total for the VU meter. One little piece of errata I forgot about was the palettes.hfile, which is simply a table of all the various palettes that can be set with the knob. It's not really human readable, so I'm gonna, well, it is, but I mean, it's not pretty, because it's just a table of colors. So I've kind of flattened what out here to take an easier look at, and you can see the USA colors. We're going to specify 16, but it's a palette 256, which means it's going to interpolate when called. We're going to give it 16, it will span that over 256. So blue, 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 and then the red and white stripes begin, and it's 16 pixels wide, or 16 bands, or 16 elements, or however you'd like to think of it. And with that initializer, it will generate a palette of 256 mapping to this, with transitions between blue and red, and transitions between white and red, and so on, so that when we scroll it, it actually works nice and smoothly. So if here is USA colors, just one of the palettes, if I zoom back out, you can see this file is really just a list of a whole bunch of them. And so the knob position, modulus 8, tells the system which of the palettes to use, and we saw individual palette element selection based on band. And that's how a band color is selected, which palette and which band within that palette. Offset by whatever the color cycling index is, as defined by the color speed, which was G color speed, as long as it's not 0. When it is 0, we always anchor here. And the reason for that is you would not want to be scrolling slowly and then have the scrolling stop with the flag halfway through down at white. So that may jog your memory if you remember us anchoring the palettes, and that was the reason why. And with that final piece of code in place, we can compile and build the project. I don't actually have a good way to screen record the flashing of the chip out in the shop, so I'll simply point the video camera at the monitor out there while I compile, link, and upload the code. Once the flash operation is complete and the camera pulls back a bit, you'll be able to see the code we just all put together up and running on the chip.
Thanks so much for joining me on this little journey. I'd appreciate any feedback, especially from other programmers, on the presentation format. I'm trying to do a top-down approach to a certain level of detail before going linear, and it's hard to know where to make that transition. It could also be that I'm the only person on earth that would find it interesting to have someone go through their code like this, but I hope not. If I'm not alone, please be sure to like all 3 parts and subscribe. Not only will that mean you'll have a better chance of seeing future episodes, but it will also confirm to me that I'm not, in fact, barking in the dark, as it were. So thanks again, and I'll see you next time in Dave's Garage.